All right, good morning, everyone. My name is Mildred, and we are having a combined live class for batch A and B. We'll start with batch B because I want batch A to have a revision of the topics that have been done previously in preparation for the quiz and rounding up the course. Now, for batch B, in week 1, we looked at the bubble sort algorithm. Now, first of all, before you delve deeper into this course, you want to understand why data structure and algorithm. Why are you taking this course? You cannot be a good software developer and you cannot optimize your code or think like a developer until you understand the different algorithms that exist. Why do we need to know things about algorithm? Once you know how to think and how to apply algorithm to your thought process, you will understand how to better solve a problem. And then you'll be able to revise that same problem to see the best way to make it more optimized. We have something we call a data structure. Now, what is the difference between a data structure and an algorithm? An algorithm is like the step-by-step process that you apply to get a solution to something. And data structure is the way or the format in which the data is stored for a particular purpose. Now, your pre-recorded video gave you details about all of this, and in the pre-recorded video, we looked at how to apply runtime to algorithm, and then looked at how to actually use the big O notation. We are going to go straight into doing the lab, and the labs that we do in the live class will help you understand better, but you need to have watched your pre-recorded video and you need to understand it at least in a basic level before coming here. So we're going to do a lab, and this lab requires that you already understand loops in Python, you understand lists, and you understand functions. Now, a bubble sort is like a comparison-based sorting algorithm. It repeatedly steps through the list and it compares the adjacent elements and then swaps them if they are in the wrong order. This process will continue to be repeated until it is sorted. Let's manually do this and then we'll do it with a code. So let's say I have this array or I have this list. We have 5, we have, let's say 2, let's say 9 and 1. What the bubble sort does is to start from the beginning, you take the first one and compare with the next. So just like the name, it will compare 5 and 2, and it's like you're bubbling the bigger one to the end. If 5 is greater than 2, it leaves 2 and it continues going. So let's see how this goes here. So let's say it takes 5. It compares 5 with and 2. 2 is smaller, and so it swaps position. 2 stays here. 5 keeps going, compares with 9. 9 is smaller. 5 is smaller, it drops 5 and continues with 9. Now compares 9 and 1. 1 is smaller, drops 1, and 9 is the end. And so in the first run, we'll have 2, 5, and once it drops 5, let's not do everything to the end. Let's see how it goes on the first run. I want you to see how it will work on the system. Let's leave it like this. On the first swap, when you're building your algorithm, it will be take the first 2, swap them, and leave this other 2. Then the next one, it compares 5 and 9, and there is no swap at all because 5 is less than 9 is in the correct place. Then the next one, it compares 9 and 1, and 1 is smaller than 9 or less than 9, it now swaps it. So now you see how it goes. So this After the first run of the swap from the beginning to the end, you will get this. Now, on the second pass now, you will compare 2 and 5. 2 is less, it's in the same position, no swap occurs. Then you compare 5 and 1. 1 is less, so let's see what the second pass will be like. 2 is less, it stays there. 5 and 1, you swap. 1 there, and then you have 5 and 9, 5, and then 9. So the second pass you have 2, 1, 5, 9. It's still not sorted. We'll do a third pass. So 2 and 1 is smaller, you swap. 2 and 5, 2 is smaller, leave it in place. 5 and 9, 5 is smaller, leave it in place. And then now it is completely sorted. And so we'll see that we have 3 passes to get to a sorted algorithm. And this is what Bubble does. It starts from the first item and compares with the next and the next and the next, and keeps taking the higher one to the end, and then start all over again until it is completely sorted. How do we implement a bubble sort? Let's create a function called bubble sort. And we have this algorithm that, let's write the algorithm here. Algorithm is, you want to say, start from the beginning or from the first index position. Compare with the next element. So the next step is, so this is how you write your algorithm for you to know how to implement it. So you say, if the first is greater than the next, you swap them. And then if the first, or let's not say first, let's say current, because we'll always check it as current. If the current is less than the next, leave in place and pick the next. And then continue 2 and 3 until completely sorted. Okay, now we have this algorithm. We want to implement a basic bubble sort. So let's say dev bubble sort. Who can tell me what will pass in here as a parameter to this bubble sort function? Anyone? Either batch A or B, anybody?
Passing the list as the array numbers.
Yes, so passing the list. So let's say we are passing in an array. We'll call the array AR. You can call it anything you want. Now, based on this algorithm, what should be the first thing we want to do here?
Count number of items in that array.
Yes, we'll count the number of items in the array. So let's say n is equal to the length of the array that was passed in. The next thing we want to do is to loop over the list, and when we are looping over this list, how do we write that loop? Does anyone have an idea how we write the loop? What are we looping through? We are looping through the array, but how do we write it? I want it to be interactive so that you will think and see why we are doing things the way we do it.
We use the for statement.
Okay, and we say for what?
We can say for maybe I in a range.
Okay.
In a range based on the length of the array.
So what would I put here? Will I put the range of the length of the array n?
I think here we're going to say n minus 1.
Okay, so why do we put minus 1?
Okay, why we put minus 1 is because the indexing starts from 0.
Yeah, but for the range function, it also starts from 0. So that logic is not the correct one. If that's the case, it's going to be range n, because in the range function, it starts from 0 to, let's say if you want it to be range 5, it's going to be 0, 1, 2, 3, 4, because the 5 you put here is exclusive. So with that logic is not correct, but it's n minus 1. I want you to think, and why do we use minus 1 here?
We're taking aside the last number first.
Exactly. Perfect. Because you are taking one out of it to compare with the next and the next. So if you don't put n minus 1, you're going to get out of range because you're taking aside the last. All right. And what do we do next to make it repeat the process? Because we say here continue 2 and 3 until completely sorted. If you want to repeat a process in programming, what is the first thing that comes to mind if you have a loop and you want to repeat that loop? So a loop is already going to do something over and over again until the condition is met, or as long as the condition is true, right? But what if you want to do the loop and repeat the loop? What do you do? Anybody?
So, to add another loop inside that?
Yes, you have an inner loop. So let's say for the inner loop, let's call it J, for J in range. So what range will the inner loop be now?
So that should skip that first item. So that means n minus 1 minus I.
Good. So we are doing this so that we will not sort on already sorted parts. And so once the first one is compared, the lower one is already swapped. So when you do this minus I is if this iterator, wherever the iterator is, you are subtracting that from it. Okay. Now we can now do the next step we want to do is we have handled the loop that will go through the items. We've handled the inner loop that will repeat. So now the logic, how do we write it here now to compare and swap? That's the only thing we need to do now.
So we now check if the current is greater than the next.
Okay, so what is going to be the current?
The current will be the inner loop, that's the J.
Okay, the current is the inner loop. If array J is greater than array, the next is array I, right?
Yes.
No, the next will not be array I.
Okay. It will be j plus I.
Yes, it will be j plus 1 because you're going next, right? So if array j is greater than j plus 1, we want to swap them because they are in the wrong order, right? So we want to make array j to be equal to j plus 1 and array j plus 1 to be equal to array j. So we can write it like this: array j, we can put on one line, array j plus 1 is equal to array j plus 1 array j. And what do we do next? What do we do next? Now, this inner loop that we have here is handling checking and repeating at every iteration of the loop. The outer loop is when this has gone the first run, then it comes to the outer, goes the second run, continues it like that until it's completely sorted. When this condition, array j will not be greater than array j plus 1, and then you want to return in the outer loop. What we are returning now is the array because now you have sorted it out. Now, is this an optimized way of writing this bubble sort algorithm? Anybody?
I think so.
Okay. Does anybody think that this is the final and the best way we can think about this? Anybody from batch B? Now, I'll tell you something, and I don't think I did this for batch A. This is a basic bubble sort. As optimized as it looks, there is another thing we can think about if you think deeply. What if this array is completely sorted already? In this case, does this actually make any sense to do this comparison? Yes, it will run only once. So that will be our best case scenario, that this array is already sorted. Right? It detects no swap after one pass, and our time complexity will be big O of n, just the length of the array. The average case is maybe half of it is sorted or is fairly sorted, and the worst case is it's sorted in reverse order. Now, this sorting is done in place, so it requires only few extra variables. But what if this is fairly sorted, this is already sorted, or this is sorted halfway, and you just want to complete it? Instead of running through the first time, swapping the first element, it works, take the second one and go, it's sorted, the third, it's sorted, the fourth is sorted, compare. Does it now optimize this? So we can optimize this in the best case where the array is already sorted. And what do we do to say, let's modify this? First of all, before we modify this, let's test this. Let's test this. Now we have, let's say, a data, and we have this list of items. Let's use and we want to Let's print the original data. And let's sort the data. We'll call the function and we'll pass the data here. And now let's print out So we have this, and let's run, and we have the original and we have the sorted, and we see it's sorted, it's working fine. But I want to optimize this. I want to optimize it in the best case where I want to do an early exit. Once it's sorted, just exit. And so we want to add something that we call early exit. And how do we add that? We want to check if it's already swapped, or we want to put like a variable, and then we update that variable. So let's do it like this. I think I'll put it better than I'll explain it. So let's say bubble sort early. Let's use this array. Now we have the same algorithm, but what we want to do is, if it's already sorted, we want to exit earlier than we are exiting. So we get the length of the array, and then we do the range for I in range n-1. We want to set a variable. Let's call it swapped, and let's call this swapped equal to false. So for now, we want to say no swap has occurred, and then we'll do the inner loop for j in range n-I-1. So it's still the same if array j that we'll put there. If array j is greater than array j plus 1, we'll have array j Now, once we have done this swap, we can now set swapped equal to true. Now we'll say if not swapped, we break. Now, why do we say if not swap, we break and then we return the array? Can anybody explain why this?
Because the array is already sorted in the
Yes.
Yeah, so when there's no swap, if no swap occurs on the first run, it just means that the array is sorted, right? So when you have this inner loop occur, you set swap is true in the inner loop. But if swap is not set to true, that means this inner loop never happened because array j is never greater than j plus 1. And so swap remains false. And if not, swap break. So you're not going to run you're not going to have like big O of n. You're not going to have like big O of 1 or big O of n square time complexity, but it will always remain your best case big O of n when the array is already sorted if you use this optimized version. So every time you write code, you can always think about how can I make it better? Now, the mistake people make is that the lesser the line of the code, the lines of the code, the better it is. Sometimes Being less does not mean better. So it's always better that your code is not complicated, but you can always look at your code and think about how can I make this better. Okay, and then you see that everything we learn in Python foundation or fundamentals is what we are using here. The loop, the break, continue statement. And so for those in batch A, or batch B, if you don't understand Python, because everything we did were MCQ quizzes, we didn't do labs in Python, but the current batch C is doing everything as lab, not MCQ, and they have hands-on programming. If you feel you are still weak in Python and you are taking this course, after week 2, for those who pay for this course, we will automatically allow you to join the Python current batch C of Python class, even if it's not for grade, but for you to be able to do it again to understand the foundations better, because if you do not understand that foundation, you will continue to struggle with this. And if you're struggling with this, you will never pass a technical interview to get those high-paying jobs, because these are the only questions they ask during interviews. All right. So we have this optimized version, adding early exit to it, and this would have answered a lot of your assignment questions already. Now, when we look at the complexity analysis, if you go to your pre-recorded videos, you understand what we use the big O notation to do, and you know why we use best case, average case, worst case. When we think about software, we always want to think about the worst case. Like when they do a test on a device or on a new technology, they always do a test on the worst case. In the worst case usage, what happens? Because you don't want to always make your system for the best case. If I say I build a laptop, the laptop batteries goes for 4 hours. That 4 hours is the worst case. That is if I play music, do games, everything. But if you're not doing those things, you can go for 10 hours, right? So the worst case is what they always put there. So that's your maximum usage. Worst case, when they test devices, they try to do a break, pour water and all those things. And in worst case, how does it spoil and this? So that's what happens. Okay? And so when we test this optimized version, let's say it's bubble sort early, and then we go there, it's faster, but how do we even check if this is faster? We have looked at how we use the time module in our pre-recorded video, which is not the best test of complexity analysis for system, but you can use it to measure your sort time. Now we have the built-in sort in Python, but when you're writing exam, they'll tell you not to use built-in method. They want you to implement, because we already have the sort function there, and the sort function will work faster. Anything that is built-in will always be better than anything that is artificial, right? You always just use the sort. But again, those functions are not going to be what they want you to use in any interviews or any exam. So bubble sort will always be significantly slower than the sorted function, because sorted function, we have, I think it's sorted in Python, that you can just use to do all the things that we did. But you're not allowed to use inbuilt when you do that. So is there a way you can optimize this, or you can modify this bubble sort to sort in descending order? Everything we have been doing now is ascending order. Is there a way you can optimize this to sort this in descending order, or you can add like a counter that counts how many swaps occur during the sorting, or you can visualize the sort by printing the list after every pass? Okay, so these are things you want to think about and say, I want to try to do all of this. Sort it in descending order. I want to add a counter. I want to visualize this. Visualizing is just like using a print statement. All right. And then you ask yourself, or you can just challenge yourself to write a function that will analyze how the number of swap changes for the best, the average, and the worst case using different input lists. And why I say this is when you write code, you don't want to do anything basic. You want to challenge yourself and say, this is ascending. What about descending? Let me see how I can do it in descending order. So can anybody tell me if you want to do this in descending order, what do you do? It's just a simple change if you want to solve this in descending order. Can anyone tell me what you can think of immediately?
Okay. For me, what I would think of is maybe starting with the outer loop first.
Yes, but that is just making the code not optimized at all. You can do that, but it's just yes, okay.
Yeah, so in the inner loop, instead of us checking if the first number is greater, we check if it's less. So
perfect. You just check if it's less. That's all you need to do. You just check if it's less, and you have done in descending order. So for descending order, all you do is to change here from greater to less. What if you want to add a counter to count how many swaps occur during sorting? So just like we did here, we put swap equal to false. You can just put swap count equal to 0. And once a swap happen here, you say swap count plus equal 1. And so that counter will tell you how many counts. And when you return both the array and the swap count. So you know that they sorted and it had 3 passes or 4 passes, something like that. Okay, so when do you use bubble sort? Can anybody tell me when bubble sort is used?
Since the bubble sort is not that fast, so I think it's for small data.
Perfect. It's for small data sets. You don't even use it in production these days. You just use it to maybe teach sorting basics and small data sets. And we'll talk about the space complexity, right? Because it's in place, it's just big O of 1, space complexity. And all of this sorting you can modify to suit your use case. And you know, one other thing I think about all of this algorithm is you want to be a game developer and you're building a game, a puzzle, something. You have to implement these things, and maybe you just modify and alter based on your game algorithm. You understand? Like if you have a game where a character is running, and when it picks something, you want to increase the life or something, and when it doesn't pick, this way you are using a sorting algorithm in a modified version that suits the kind of app that you are building. So people who need to know this thing the most are people who want to be innovators. You want to create a game, you can now think that I can do it in a certain way. I want to swap if this particular character does this, I want to change the color from red to green, or the character is about to die, picks up something that is like a fuel that adds life, or change it to green. You know, it's like a swapping you're doing. At this point, you can't use the sorted function in Python, but it's something like a bubble sort. I don't know if you understand what I'm saying.
Yes.
Yeah. So knowing this thing even helps you to be an innovator, because there are things that you want to invent that is your own invention, that now you have a wide range of knowledge to think about what you can do. So you can modify anything from the norm to do it. Innovator just means you're inventing something new. And so which means that you can use what exists to change things. Now this is where we end for batch B. Batch B, you can stay on to see the parts that you get to, and we're going to look at the tree data structure. Now, for the tree data structure, let me just create tree live.py. When we talk about tree, what's the first thing that comes to your mind when you talk about a tree? You go outside your house, you see a tree standing. What do you see? You see a whole roots, you see the tree up, you see many branches, you see several leaves branching out at different points and leaves. You remember your family tree, and you see that it branches out at several points. You see the great-grandparents or your forefathers, or let's start with your great-grandmother and your great-grandfather. And then these are the roots and the parents. Or you just want to look at your maternal tree. You look at your great-grandmother, and then the great-grandmother has several children. And then the great-grandmother gave birth to children that have children that have children, right? And you want to just look at only the branch about your mom. And so you look at your great-grandmother had your mom, right? Your mom had you and other siblings. Then you want to look at your own branch you had. So every place is a subtree of that parent branch. So the tree data structure is just like that. It's not like the other data structures that we have seen that are all linear. When we say linear, they are stored sequentially next to each other. But for the tree, a node can branch out from several places, just like you have the tree that you see outside with branch and leaves from all angles. And then you can take a particular branch and all the leaves there are the children. That is a subtree. And then you can follow the tree stem and go up and you see another branch and you see several leaves. That is exactly what the tree data structure is. It's non-linear and it's a hierarchical data structure. So things are in hierarchy, and we know the kind of apps we can build with the tree data structure. As a matter of fact, for those of you who are doing internship and who are staff, we are building our apps with these data structures, both the tree and the hash tables, and we're going to see more complex ones that we use to do innovation. Now, when you have a tree data structure, we have something. Let me get an image. I hope I have these images here. So we have this, like the image here. Each element of the tree is called a node. This is a node, 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 this is a node. The topmost one, A, is called the root. So the root is usually the first node of the tree. Then when we say edges, we mean all of these lines that connect it. So we have, this is an edge, this is an edge. So these lines are called edges. When we want to say the parents of a particular child, so this A is a parent of B and C, right? And then this B has a subtree, is a parent of D and E. So you can see, and C is a parent of F. The parent has a link, direct link to his child. The children of a parent are the ones that have a direct link. When you get to something like these last ones that don't have any child or anything, we call this a leaf node. When I say the leaf node, you just mean anyone that doesn't have any link to any child. Then the height of a node is the number of edges between the node and the leaf node. So edges are these lines, right? So we want to say the height of this node A. You count 1, 2, 1, 2, 1, 2. So 2. So you want to see the maximum number of edges. So assuming there's another line coming down here, so it will be 3, because you say here is 2, is 2, is 2, they're all 2. So you now say this is 2, the height of the node. The same thing as saying the height of the 3 is the maximum number of edges from the root node to the leaf. Like the height of the node B is 1 here, because it's 1, right? And the height of A is 2, which is the same thing as the height of the tree, because it's from the root to the leaf. How many edges? You will go on all sides and see which is the maximum number. The size of the tree is a number of nodes. So you count 1, 2, 3, 4, 5, 6, the size of the 3, 6. So you know the different terms that we're going to use. Now there are different types of trees. We have the general tree, we have the binary tree, we have a binary set tree, we have a full binary tree, and the binary set tree is a tree where the left child, so if it's a binary set tree, this left child, the value here will be less than the parent, and the value of the right will be greater than the parent. Even down to the descendants, the value here will always be less than this, and the value here will be greater than this. But generally, everything here will be less, everything here will be greater than the parent. And this is what we'll look at in week 10. So we'll not go into binary set tree this week. The full binary tree, every node has 0 or 2 children. A complete binary tree, all the levels are filled except maybe for the last one when it is filled from left to right. And then we have a perfect binary tree where all internal nodes have 2 children and all leaves are at the same level. And then we have what we call the AVL tree, which is a balanced tree. We'll also look at this in week 10. So now let's look at the binary tree representation in Python, and I'll see if I can come up with a lab that will not just repeat what we have in the pre-recorded video, so that you can watch the pre-recorded video and get deeper insight from the live class. We already know, if you have watched the pre-recorded video already, that we create a node class, and the node class is just going to take the data. So that's what we always use to create a node in the tree. The way we create this is totally different from the way we would have created our normal object-oriented programming. We just create a basic class, and then outside the class we create the functions, not within the class. And then you see how we do it differently when we want to do a balanced tree, or we want to do a binary set tree, and how we try to use private and public methods in week 10. So you need to understand week 10, come back to week 9 to get deeper insight. And I'm trying to see if we have enough time. I might even do week 10 live already, so that next Saturday we'll see how we want to implement this for something else. I'm trying to think of something, a real world application for this. Let's say, but before I go further, who can tell me what you can think about when you think about binary tree? What kind of application can you think about this tree data structure? How does it, which application can we build with it that will make sense? Anybody?
I don't know how the logic would be, but from the research while I was watching the live lessons, the class lesson, I found out that it would be helpful, effective for file explorer application, file management applications.
Yes, it's very good for file management, even organizational structure. If you want to do like organizational diagram, the flow of things. And even, it can even work for like to-do list. Like if you see, I will have GitHub, right? And you have different tags and different tickets for different issues for an app, and you want to set whether one particular issue is a blocker for another one. This has to be done before this, and you want to set whether this is a bug and this is something, and it creates the hierarchy of what should be done first, priority. You can now put even a priority queue, like which should go first. And when we talk about this, we saw it last week too, and there's how we can implement a tree where, when I say priority, I mean when, let's say we have a general, like a primary health clinic, for instance. Let's say how the tree works. When a patient is classified as priority, they move straight to maybe a particular, give that one a bed first, and then maybe the flow of how things will work, because they have a flow, right? People walk in the place. Priority is if there is nobody, life and death situation, they go with the children first. and then they start going with the adults according to age. Children take priority in triage. But when they triage and somebody has more, and then they change the flow, instead of from the emergency room to the triage place where the nurse takes the vital sign, then move the person to any unit that person is supposed to see, maybe the general physician before they begin to. So in that general physician office, whatever the case, maybe the family physician will see that, okay, this is a case for the neurologist, and branch out somewhere else, and the next person branch out somewhere else, and the next person, it just keeps referring to different places. So you can see that the flow is not fixed. So you can have a tree where you say, if this is the case, this is the direction. If that's the case, that's the direction. If that's the case, that's the direction. And you can see that from one route or one source of the person who is the referring physician is sending everybody to different places, creating different branch of flow. And so if you are building a system where the physician doesn't have to decide, and the system will decide and give a number, like, so you see things like in the waiting area, you see PO1, SO1, and you know what P, any number that is prefixed with P and S means, you know that, okay, this PO1, they're going this way, S go this way, and they know who to call. And on the mic or in the office, the physician sees only the numbers that are relevant to their own practice or the patient. So you see how they have a different tree branching out from the same center, but sending them to different directions. That is one way you can build a tree data structure. And so when you want to search for someone, you don't have to go around the whole hospital. You just go to the root of the referring place, and you see the branch where the person followed, and you just follow that branch down. So the person came here, went straight to neurology, went straight to the neurology ward, and from there you can go to the neurology emergency. So you follow one branch instead of bouncing all around the place. So you understand what I'm saying now?
Yes.
So you can use this for both a priority. You can actually have a priority queue that branches as a tree. So a lot of data structures can be combined. So you see why it's good to know this, because sometimes there are no inbuilt functions for you to innovate or invent things, but you can use the inbuilt functions and module to make it faster. So if there's, like when we do the breadth first search and we see that we just use the queue data structure, so things like that. So now we want to do something like let's say we are doing I don't know if anybody have seen this app, Wolfram from Alpha. In fact, if you studied mathematics in school, you will know what Wolfram from Alpha is, because any kind of expression you put in that Wolfram from Alpha app, it will just tell you the answer, build you the graphs, anything. That's one thing people used to cheat in mathematics, or verify answer. If some people are lazy, they don't want to do the whole working step, they use Wolfram from Alpha and it solves all your mathematics questions, or you just use it to look at the different ways you can solve a particular thing. So let's build something like that app. Let's build an expression tree that will evaluate maybe algebraic expression, things like that. So let's use it for mathematics. It will make more sense in mathematics. So we'll do an expression tree, and for this tree we want to know what the root is, the left value, the right value. Let's say for this expression, I want to do something like, let's come up with something a little complex. Let's say 3 plus, let's say 5 plus 9. 5 plus 9, and we want all of this again. So let's make it more complex. We want all of this again to be, so 5 plus 9, and we want 5 plus 9. Let's multiply this by 2. Something. Let's stop here so we don't confuse ourselves. If you do an expression tree, what do you think when we create a tree data structure? What do you think we want to use as the parent nodes in different parts of the tree? Like you see, for instance, we have the BODMAS, well, the brackets of division, multiplication, addition, subtraction, right? I want to see which one takes priority, everything in parentheses. So we are handling this parentheses first, right? Everything in this parentheses. Within the parentheses, we want to handle what is in parentheses first. So what is going to be the root is going to be the first expression plus, because now the parent is going to be the the sign, and then the children, anything less, or we can just put 5 as the left child, 9 as the right child, because 5 is left of plus and this. So let's build a class that we can use to always solve expressions like this. So let's do that, so it will make us understand the tree properly. So let's call this class, I'll call this class expression node. And we'll create the method in it, and so now we want to say self.value is equal to value, and we want to self.left is equal to none, and then the right. Okay, so we have these here. Now this is just, we just build a class, we don't have any method in this class. Every of our functions we are going to build is outside the class. So there are some apps that you build that you just have a class like this just for you to create a value, but you do not have any methods apart from the instance method within that class. So I will create a function that I will use to do evaluation. Let's call this function evaluate, and we'll just pass in the root. Now we want to say if that root is none, we just return 0, right? But if that is not the case, we want to look at the left and then look at the right. So we say if root dot left is none and root dot right is none. So what do we do if both of them are none? We want to return the value of the root. So if the root is none, return 0. But if there's a root, we want to check the left. If there's nothing at the left and there's nothing on the right, you just return the root. So we'll return, let's always make it an int, we'll cast it. Because when we pass things, it's always a string. So we return the root value because it doesn't have left and right. But we want to evaluate the left and the right subtrees once we have established all of these checks. So we said, let's say the left value will now be equal to, we will call this function evaluates. So just like we're doing this recursively. So let's call the same function evaluates. I'll see if there's a better way to think about this. Root of left, and let's do right value. Let's say right val is equal to evaluate root dot right. Let's say I'm trying to think about how this will make more sense. Okay, so we have the expression node, the class. This class is just for us to add the value to the tree. And then we have the evaluate function. It's not part of the class, so take note. We're just creating a function outside the class. And for this function, we want to use it to run the evaluation. When you're running an evaluation, you want to see what the root is. If there is no root, just return 0 because it's 0. If there's a root, you want to check the left. If it has no left and it has no right, then you want to return the root, the value of the root. By using dot value because when we create that node, we already passed the value here. And the left was set to none, the right was set to none. So if it remains none, you do that. But if something has been added to it, we're going to evaluate it. So we're going to evaluate, but we are going to do it recursively. So we'll call the same function within itself here to repeat the left root. So we're doing all of the evaluation on the left, all of the evaluation on the right, gets the result, and then let's apply the operators. So for this expression tree, let's work with this function we're creating. We're creating this function without knowledge of what expression we are going to be handling, right? Hold on. So we don't know what expression we're going to handle, and we're creating this without that knowledge. So let's just do basic ones like plus, minus, times, addition, subtraction, multiplication, division. Let's create operators within this. So let's say if root dot value. Now I told you earlier that the root will be all of the operators. So if the value of the root is addition, sorry, I'm thinking about this as I'm working, so it's not the best way to think yet until we review it. So if the value of the root is plus, we want to return the left val plus the right val. If the value is equal to minus, we want to return the left val minus the right val. And if the value is equal to multiplication, we want to return the left val times the right val. And if the value is equal to division, we want to return the left val divided by the right val. So you can do more expressions here for as much as you want. You can put exponentiation, you can put floor if you want to round, like that. So let's build an expression tree for this one here. So now let's say this is the function that we have created. So now we want to work on this. Let's build an expression tree for this. So now we have created all of this and we want to make this a tree data structure that will evaluate this expression. Let's do it manually. We'll now have 3 plus 5 plus 9 is going to be 14. So it will be 3 plus 14 times 2. So the next thing we'll have is 14 times 2 is what? 28. So it will be 3 plus 28. And then when we add this, we'll get 31 as the final answer, right? So this is what we're expecting to get when we use what we have created. So let's see if that will work. So let's start creating the tree. Does everybody understand what I'm trying to achieve?
Yes.
I don't know if you have something like this in your notes. Have you gone through the notes?
Yes.
Yes.
But my
Yeah.
confusion.
Okay.
Roots.
This root?
Yes, my confusion is the roots. How do we place the roots? Like from the expression, how do we point out the roots?
The root is always the expressions, the mathematical symbols. Will always be a root. To the left of the root will be the left child. To the right of the root will be the right child.
I mean the root A.
Oh, here?
Yes, root A. Yes, that's the first node. I mean.
Yeah, the first note you said it as root. So, like, for instance, let's say for this kind of expression, the first node is root. So you say root is equal to, you call your node class node A. So you have set this as a root. Then the left child of the root will be now root dot left, right? And what is on the left? B. So you create a new instance B. So now you understand it. And then the right side of the root, you make it root dot right. And this will now be node. So we're doing what is in the pre-recorded video of we have a node class. I'm not using this. So let's say, assume we have a node class that already has, that will take the value. So the node class is just something like this, but we are using, it's like exactly like this. Actually, you have the value left and right. So you put the value here. When you call node, you pass it the value. Now, in this case, now we've done the root, the left, and the right. Now, this root.left b, so let's call it here root.left. This root.left has a left, so say root.left.left, right? And the left is equal to node d. Now, does it make sense? Now, the root.right that we have done here, root.right, this root.right, well, I mean this root.left also. Let's finish with the root.left first. So root.left also, this b has a right child, and the right is equal to node e. Do you understand it now? And then the
Yes.
root.right that we have, that is c. So you say root.right, which is c, has just a right child. So the root.right is equal to node c. So you have built your tree. So this is how we build that tree, assuming we have a node class. Assuming this was like class node, not expression node. But, we have this class there, and so we call an instance of the class. So everything is like an instance of the class. So you understand how this is done now?
Yes.
So this is,
Is the last one F or C?
sorry, F. Yeah, so this is what we have built this tree. So in a tree you have, you always start from the root. So you want to,
It's,
You said?
sorry. So at this point, what if we have the fourth stage of the tree?
okay, so if you have the first stage, you continue. Let's say here you have this D has a left child, for instance, and let's say the left child is G. So we now come, what is D here? Root.left.left, right? So root.left.left has a left child, as dot left is equal to node G. So you understand the pattern now that it goes
Yes. So that will continue like that.
to continue like that.
Okay.
Right? And if you are confused, you can give it a name and say this is the root. And you want to put first left. And so here you can come to say first left. Dot left. You understand? So you can put the names, like if you are practicing, you can put the name, but it's always better to follow this convention. If you are practicing, you can put the name so that you won't get confused, just to understand the flow. So now that you understand that, let's build this expression tree. So now we want to build a tree, and you have this expression that you're building the tree for. So I said that we want to focus on the mathematical symbols. Now, when we look at this, what is the first thing we're going to evaluate? The parentheses, right, from mathematics. And in the parentheses, we have another parenthesis. So the first root, the first parent will be plus. And so let's start like this and say the root now is equal to, the name of our class is expression node. So we'll say root is equal to expression node, and our root is addition. Now, when we get this addition, the left is 5 and the right is 9. But is that what we are going to do? No. Why are we not going to do that? This root here is plus, right? And we are looking at this whole parenthesis. We're not going to look at what is here for this parent. We're going to look at what is outside. So we have this plus here, and on the left side of this whole evaluation, we have the number 3. I don't know if you understand what I'm trying to say. So let's say 3 plus 5 plus 9 times 2. I'm trying to look for a way to make it more, that makes more sense for me to explain it. Let's change our thought process, maybe to make it easier. Let's not evaluate it with what has priority. Let's evaluate it using what is the first symbol. So let's say the root is this first one, is the root, right? So we're using the first plus. To the left of this plus, we have 3. So let's say root dot left is equal to expression node. We have the number 3. Now we're sending this in a string, and that is why here we casted to an int. If you see here, when we're evaluating, we cast everything to an int. So to the left of it is number 3. Now what happens to the right of this? So to the left is 3 of this plus. This is what is to the right of it. Now how do we choose what is to the right, since we have all of this expression on the right? We now look for the highest order, right? So we have 5 plus 9 is evaluated in a parenthesis. We are looking for here, the right here, which is going to be the parent here, is the multiplication sign. So say root dot right is equal to, this will take a lot of thoughts, and I hope if we'll test this to see if it's correct, because we want to get 31 at the end, and then you will build your thought process like this. It's a little complicated to think about. Now we have all of this has the different parents. We have the root has plus, we have the left of this plus to be 3, and on the right side we want to have a parent on the right, and on this right side we have a lot of evaluation that are children. On this right side, we'll say we use the multiplication, because this multiplication has a left child, which is 5 plus 9, and a right, which is 2. So we do it like this. This is the left, this is the right, and we want to now have what is on the left side of the right, because this root, let's look at it again. This root has 3 on the left. We're finished with this left side. There is no more. We're on the leaf node here, and on the right side we have more evaluation. So this right now, we need to have a parent for this right to have a left and a right. So we have multiplication. On the left side of this right now, so let's say root dot right. So we're on this right, on the left side of this, we have 5 plus 9. So that means we're going to have a parent, which is plus. And then the child on the left will be 5, the child on the right will be 9. So we'll say expression node. The left is going to be the plus sign. And then the left is plus, the left of the left is going to be 5. And so we're just working on this part now. So we'll say this left has a left that is equal to expression node 5, and it has a right that is equal to 9. I hope this is going to work out well. And then we have the root dot right, because here we did root dot right dot left to be the plus sign. So say root dot right dot left plus, and then we have 5 and 9 for the child. And then on the right here, which would now be root dot right. No, we did root dot right is this, and then the left part we handled, and I want to do the right. So it's going to be root dot right dot right. So this root dot right is multiplication, so the right side is 2. So dot right is equal to expression node and 2. I hope this works. Now let's print out this and see if it works, and see if our thought process is in the right place. Let's say result of expression will be equal to evaluate root. So we could just pass in the root to evaluate that. And let's run. And we got 31. Wow, it works. It works. Now, do you guys understand the thought process?
Yes.
I understand the tree, but it's deriving it is the issue.
Yeah, thinking about how it goes, right? So it's something you have
Yes.
to write out and manually work out. So you see, writing this evaluation, right, like this, what are the things to the left and what are the things to the right? So you can say I have this plus. To the left of this plus is 3. To the right of this plus is all of this. This is another sub 3. So that means you have this root and you have the left, and then you have the right is a whole sub 3. Now to the right is a sub 3. What is going to be the parent of that sub 3? Let's take the middle or the multiplication that has higher priority. And so to the right we'll put the root of the right, and then we'll handle all of the children of the right. To this right we have a left part. The left part we have 2 children, left and right, so we have to have a parent for it. So you want to be dealing with the parents before the children. So that's the whole logic. So this is one thing I wanted to go and manually practice before you get the logic. Once you get the logic, it will never leave you. So if we do the complexity analysis here, when we want to traverse through this, the time complexity is going to be big O of n. When we want to insert, will be big O of the height of the tree, big O of h, the height of the tree. If we want to have search, you see the same based on the height. If we want to evaluate, it's going to be big O of n2. So you can modify this thing to take floating point numbers, and you can extend the expression tree to handle exponentiation like this. So you can practice with this.